Hello, how's it going?
Hey, Alan, how are you?
All right. How's everything with you?
Good. Trying to get some sleep.
I bet. Yeah.
I think I was a zombie the last
Sure.
week.
Oh, I'm sure. Absolutely. Yeah.
I was
So is
I was catching up though, and I just watched session six, talking
okay.
about well, basically, I'm looking at the homework, and I just had a question for you.
Yes.
Uh, Section questions 9 through 12.
Uh-huh.
Are you just looking for the definition of, so you ask like, what is the payoff to the buyer of a call option, like, and so on
Yes,
and so
just the
forth?
def
Okay.
yes, the
Okay.
formulas. Yes, that's right.
Oh, you want
Yeah.
the formula?
Well, yeah, I mean, well let me look and make sure I know what you're referring to. Let's
Yeah.
see. Um so let's get this thing open.
Yeah. 9 through 12.
All right.
Yeah, it seems like everything here you can do in the Excel,
Right.
like part two problems. That's all in Black Scholes examples template.
Right. So um yeah, just the actual formula. In other words, for the pay,
Oh, okay.
remember,
I mean, we could.
and
That's in the template that we have from the previous homework, so that's fine.
yeah, like the pay after the buyer of a call option is max S minus X and zero.
Yep, I
That's
gotcha.
what.
Because I was putting in the actual definition, like, difference in the underlying asset of the spot price
Oh
versus the
no,
strike price. Okay. Put in
that wasn't
the
really
formula.
necessary. All right,
Okay.
and this was the last one, so I'll be finishing them up this weekend. And then we'll have grades ready probably by Monday because there were only the six assignments anyway. This was the last one.
Okay.
Just because the material the last couple of weeks is a little bit more
Yeah.
not it doesn't lend itself well to assignments. Let's put it that way.
What
So
is the deadline for this one, for this homework?
oh, you this number six, you mean?
Yeah.
Well, ideally, as soon as possible. Now, the school expects me to have your grades ready within 3 days after you have your last session, but
Okay.
it's a
I can get
little
this to you
loose.
tomorrow.
All right, that's perfect. Yeah. Technically, let's see, Thursday, Friday, Saturday, Sunday. Well, that's Sunday, so that means Monday really would be fine.
Okay,
So,
great. Thank you. Appreciate
okay,
the
sure,
the wiggle room there.
no problem. All right. Now, this week, the topic this week is a little bit different because what we're doing is we're sort of veering over into the world of risk management, which really what all these derivatives are used for is managing risk. So it stands to reason that we would spend at least some time analyzing how risk can be managed. And we're going to be introducing the so-called value at risk framework, which was introduced about 30 years ago as a way of fairly easily calculating the risk of an entire portfolio of assets, regardless of what's in that portfolio. So we'll discuss that as we go along. But um, there's a lot of Excel examples for this one. So we're going to open these up right now. And all right, here we go. Gotta get this open. What's happening here? Doesn't seem to want to cooperate. No, it doesn't. Oh, here it is. Okay, no wonder. All right, so let me get these open now. So this is actually this week, a lot of the material is based on statistics more than anything else. So luckily Excel is excellent with statistics. It has all those functions built right into it. And so we'll be able to take advantage of its capabilities in order to calculate the numbers that we're looking for. So let's see. So here's yes, good. Yes, let's get this open. Go. Now value risk, this is the first actual value risk example. And it's all been set up so that we can fairly easily enter the information we need. And then the expected shortfall example is a bit of a extension of value at risk. Just take a look at that. And then the normal distribution. I just wanted to give a brief review of the normal distribution in case anybody hasn't been exposed to this for a long time or possibly never. So let me get all these open. So, in finance, a lot of our results are based on the normal distribution. It's pretty normal or common, I should say, for us to assume that the returns to a portfolio of assets are normally distributed. And so that's the case here as well. All right, let me get these open. So if it's been a while, the normal distribution is represented by a curve. Let's get that open. And let's see, where are we? No. All right, so let's quickly run through the normal distribution. We don't have to go nuts, but so the normal distribution is a probability distribution, which has some very important features that make it very attractive for financial applications. You often see it illustrated with the so-called bell-shaped curve, which represents the curve itself. The height of this curve is used to give us the probabilities of certain events occurring. So the normal distribution is characterized by a mean, or the center of the distribution, which is often designated with the Greek letter mu, and the standard deviation, which is a measure of risk or uncertainty. And it is illustrated, or usually it's described with the Greek letter sigma. Okay, so you could, for example, have an example where suppose that we have a stock in our portfolio. And they're normally distributed. And that assumption, by the way, is made in the value risk framework. The returns of the stock are normally distributed with a mean of 10% per year and a standard deviation of 30% per year. What does that mean? All right. Well, basically, the way to think about it is that you're being told two things. What is the average return, which basically refers to the center of the distribution? So I'm going to convert those into decimals. So 10% becomes 0.10. Now, the standard deviation tells me how far away on average the returns are from the center. So if 30% might be a very large amount of risk for a stock. So let's say that this tells me that the spread between this mean and the standard deviation means that there's a very high probability that the returns to our stock will actually end up being somewhere between a loss of 20% and a gain of 40%. So in other words, this particular stock has a lot of risk involved. So this area here covers roughly 68% of the curve. And so, and that's one of the properties of the normal curve. So if I own this stock, I can make statistical statements like there's a 68% chance that my actual return will be between, let's say, a loss of 20% and a gain of 40%. Okay, now with another stock that has a smaller standard deviation, you're going to get a lot less spread between these values. So let's say with another stock, we have another stock with a mean of 10%, but a standard deviation of only 10%, let's say. So what that means is that the spread between these two values is much smaller. So in other words, there's a 68% chance with this stock that the actual return is between 0 and 20%. So in other words, you can see that this stock up here is actually riskier than this one because the range of possibilities for the stock up here is quite a bit higher than the one down here. So the standard deviation can be thought of as a measure of risk. The larger the standard deviation of a stock, the more uncertain its returns are, or I should say, are its returns to be proper English, and therefore the riskier it is. Okay. So we think of the mean or the mu or center as the average return, whereas the standard deviation tells me essentially how far on average the returns might be from the center with a given level of probability. So now what's interesting about this normal distribution is that it's symmetrical. About the mean. So that means that in this example, the probability that the return is between 0 and 10 is the same as the probability that the return is between 10 and 20. So in other words, I actually had another color here so it's more clear. This region, oops, what happened? Does not want to cooperate. Let's see what's going on. Here we go. So there's this region here and this region here have the same probabilities, okay? Because, again, of the symmetry of the distribution. And that's an important detail. That really does help us derive a lot of important results. This principle of symmetry means that there's a balance on either side of the mean, so that extremely large losses are balanced off by extremely large gains. And so this is a very popular probability distribution to use to represent rates of return to stocks and other assets. So in Excel, it has all of the capabilities we need to really calculate anything we need based on this normal distribution. Now, in the value risk framework, and there's more. These are already on Brightspace. You can go and look at them if you want. I have more detailed examples here, but in the value at risk framework, we're going to assume, like with so many other models, like Black-Scholes, as a matter of fact, that the returns to a portfolio or a stock are in fact normally distributed. In fact, that's kind of the heart and soul of this whole value at risk framework. And so the value at risk actually has a very interesting history. And in fact, let me see if I did mention that in here. Maybe not. I'll tell you what, let's take a bit of a detour into the history of this value at risk framework and the reason why we're using it, why it's so popular today. So the value at risk framework, and it's often abbreviated PR, as you can imagine, was invented at JP Morgan in the early 90s. Now, what was the motivation for creating this thing? One issue that faced all financial institutions was that there were risk measures available for different financial assets. Sorry, the measures for different assets, such as beta for stocks and duration for bonds. And actually, one that we know from last week, and delta for options. The problem with these measures is that these measures were not, and still are not, directly comparable to each other. So that means then if you have, if an investor has a portfolio or had a portfolio consisting of all three of these assets, it was not possible to express the risk of the entire portfolio with a single measure or a single number. And that's kind of a big deal, especially you can imagine like you're running a big trading desk somewhere at one of these gigantic hedge funds or whatever, and you have traders trading currencies and others trading bonds and others are trading stocks. You know how to measure the risk of each individual team, but how do you know how much risk the entire company is exposed to from your proprietary traders? So there was always a need for some measure that could actually be applied to all these assets at the same time. And up to that point in the early 90s, it had not happened. Okay. So the measures that were developed, like beta for the stock market, were all designs for one specific class of assets, and that was it. And there was no intention to make them comparable directly to each other. So the value risk framework made it possible to express the risk of all assets with a single uh, measure and thereby combine them, the risks of different assets, into a single number. Now, the method itself is actually surprisingly straightforward. You makes you wonder why nobody thought of this sooner, but another motivation for the value risk method was to create a relatively simple framework that could be understood by non-specialists. Like, in other words, imagine yourself trying to explain to the boss at one of these hedge funds, here's how much risk these currency traders are taking on. Well, it was meant to be as straightforward as possible. And so now JP Morgan had an ulterior motive for creating this measure. They had all these clients that they were actually being paid to manage their portfolios for. Okay, so in other words, I guess if you're like a relatively small financial institution, you don't have the expertise to manage your own investment portfolios. You can turn to an investment bank like JP Morgan and ask them to do it for you for a fee, of course. And so what Morgan was trying to do here was the value at risk framework is straightforward, but it requires a great deal of data to implement it properly. So you can see where this is going. The goal, JP Morgan's goal, of course, they actually let the clients use the software for free. But in exchange for the clients paying for the data that was being used. So in other words, they were trying to sell data. So that was their motivation, not the framework itself. I mean, I don't think they even copyrighted the thing. All they did was say, listen, we have this new framework that we can use to help you manage your portfolio. And, you can use it if you want. You can use it on your desk. We'll give you the software, but you'll need a lot of data to work this thing properly. So they were hoping to make money by selling data. So now, interestingly enough, value risk was eventually split off and turned into an independent company called RiskMetrics. And while they were a separate company, they published a lot of free research online. It was possible to look at all this documentation and understand exactly what they were doing. But that didn't last very long because eventually Riskmetrics was sold to Morgan Stanley. And what I think they still own Riskmetrics. And now, realistically, if you want to get information about value risk from Morgan Stanley, you have to be a client. Okay, so in other words, nothing's for free here. But so the value risk framework was designed to be a relatively straightforward way of measuring risk that could be applied to any asset in the economy, although it was more appropriate for some assets than others, as we'll see as we go along. So the entire framework was based on what's called modern portfolio theory, which was developed by Harry Markowitz in the early 50s at the University of Chicago. Here's the interesting part. He was actually a PhD student in the economics department at Chicago. Now, this is at a time when they had, like, Chicago has a reputation for having the very best economics department. They've had more Nobel Prize winners, I think, than still any other school. They had a lot of the big heavyweights like Milton Friedman and Gary Becker and all these guys who were pretty much all hardcore free market economists. So that's what they were known for. Now, Markowitz comes along and, the tricky thing about getting a PhD is trying to find a proper dissertation topic. So when you come right down to it, portfolio theory really is finance more than economics. And, when he presented his dissertation, apparently there was a lot of discussion about the committee members, whether we should give him this PhD, because this isn't really economics at all, but cooler heads prevailed and he was given his PhD. And then in the early 90s, I think it was 1990, this framework proved to be so valuable and helpful, so important in the history of finance, that in 1990, Markowitz was awarded, you should probably guess, the Nobel Prize in Economics. He taught at Yale for all those years. I think he might still be alive, but I'm not sure. I have to look that one up. Maybe not. So anyway, so it has an interesting history. So and modern portfolio theory itself is based on the assumption that the returns to stocks are normally distributed. Okay? And so we can develop a framework that tells us how much risk is involved, and it is just 100% based on statistics. That's it. No financial statements or anything like that. It's 100% based on statistics. So that is at the heart and soul of value at risk. The value at risk sort of leverages off of this to give us a new framework that can be applied elsewhere besides just stocks. But we have to be able to assume that they are going to follow the normal distribution. Now, value at risk methodology is based on the assumption that all assets, the returns to all assets, are normally distributed. Now, this assumption works well for some asset, such as stocks, but not as well for other assets, such as bonds and options. All right. So you're kind of pushing your luck when you apply that assumption to stocks and bonds. So the way they work around it, they have I guess you could adjustments to the formula that you can use to sort of dance around this a little bit. But the whole point of this is that you're suddenly able to put together this framework, and now you can say, at the end of the day, here's how much risk is in all these portfolios that we're managing here. And, you'd think, well, it's based on so many unrealistic assumptions. Maybe it's not a terribly good framework, but here it is 30 years later, and it's still being used by all financial institutions. Okay. Now, I'm sure they're taking it with a grain of salt, but the beauty of a setup like this is that financial institutions can use value risk to set trading limits for their proprietary traders, because you can actually have individual limits on the individual desks, and yet you can see how the whole thing is impacting on your financial institution. So now I briefly worked at a German bank called Westdeutsche Landesbank, where they did exactly that. The traders would have you come out in the morning to be a printout. They would say, all right, so the currency traders have used up this much value at risk, their limit is this. And so that is how they know how much risk they can take on during the day with their different trades, by basing it on value at risk. Okay, it's a very common, way of doing this, as opposed to simply saying, here's $1 million, you trade it, hopefully you don't lose it. Instead, they have value at risk numbers that they all have to live up to. So now we're going to go back now into the slides and see how this framework is set up. Now, when you look at it, you'll say this is kind of simple looking. And so basically what it's doing, the measure itself is telling us how much we might lose over a specified time horizon with a given level of confidence. Now, that level of confidence is often set at 95%, but it could be different than that. If you're really worried about risk, you might set it higher at 95 or 99%. If you're not quite so worried, you might lower it to 90 or something like that. But normally, the level of confidence is either 90, 95, or 99. Those are the most common ones. And again, I worked at a place where they're horrible, absurdly conservative, and their value at risk was set at 99.9%. But a portfolio like that is going to be so safe that it's never going to make any money. So this would be for things that are absolutely, you must not lose this money. Okay. So anyway, so it makes it possible for us to have measure the risk of stocks and bonds, but it also gives us the ability to say, well, listen, if I bought an option for this portfolio, what will that do to the risk? All right, now we know what the delta is. We know how much, for example, if we're told that an option has a delta of 0.5, we know that that means that if the stock price goes up $1, the option will gain in value by 50 cents, let's say. But what we can do is define measures that will show us the impact of changes in market conditions on not just the value of the portfolio, but the trade of hedging instruments that we're using, so we can recalculate the value at risk at the end of each day without it being too horribly time consuming. Because time is a real headache for the value at risk framework. One of the real drawbacks, I just want to mention that here, of the value at risk framework is that besides potentially using unrealistic assumptions, it requires a great deal of data and is extremely time consuming to calculate. Back when I was telling you about Westdeutsche Landesbank, what they used to have to do is, in order to get those numbers for the traders in New York City in the morning, the computers in Germany had to run all night just to get the numbers that they needed for the next morning's trading in New York City. And they had a huge bank of computers running round the clock. They weren't skimping on their spending on hardware, but that's because they had a lot of assets in their portfolios. So it's a very time-consuming process. So now, if you're probably wondering, well, why do we keep using it? Here's a side note. There are some approximations that can be used to speed up the calculation of value risk. But these, of course, are based on typically unrealistic assumptions. So in other words, you have to ask, there's always going to be a trade-off between speed and accuracy. You can't have both. Either your framework is accurate or it's fast, or it can't really be both. So you have to understand how much you're trading off when you try to have more speed versus how much accuracy you're actually giving up. All right. So, as we mentioned earlier, stocks, you probably heard the term beta. The beta is a measure of the risk of a stock, and duration is the measure of the risk of a bond. For options, we have measures like delta and gamma, which we discussed last week. So, but it's a very surprisingly simple idea. Imagine we had this setup where there's a pension fund that holds $100 million worth of IBM stock, and we're told that on average its losses should exceed $20 million once every 20 trading days, or 5% of the time. Or you can think of it alternatively as 19 out of 20 trading days, our losses should not go past $20 million. So there's a diagram here somewhere that represents this. Yeah. So what this is telling us is that with the mean value of the portfolio at $1 million, if our losses are not going to exceed, oh, these are different numbers. I didn't realize that. Okay. Let's see if we can sneak this in here. Here's your normal curve for the entire portfolio. Oh, I forgot. This is PDF. PDF works a little differently. I find that PDF is surprisingly awkward to work with for certain applications. You gotta go look up like the right template or some nonsense. I don't like PDF. You know what? It works to a point, but I find it to be a royal pain to use it. All right, well, that'll have to do. See that it's a straight line, come on. All right, I'll tell you what, let me move this somewhere else. This is ridiculous. I just don't like PDF at all. So what we're trying to illustrate here is this. The portfolio is worth $100 million. So the center of this distribution is $100 million. I'll abbreviate that MM. And then they're telling us that 5% of the time, which is this left tail, by the way, the area under this curve is equal to 1 or 100%. So this 0.05 means this is something that should only happen 5% of the time. Okay, this is like, think of this as the worst case outcome for a portfolio. The bottom 5% of the time, just like the bottom 5% of a class with their grades. And so they're telling us that we've already determined that that maximum loss is going to be 20 million or possibly more. And that would bring us down to a portfolio that's worth a maximum of $80 million. This number that you're seeing here is our value at risk. So we can either express it as 5% value at risk, or sometimes it's called value at risk with a 95% confidence level. It means the same thing. So you're basically looking at the left tail of the normal distribution when you calculate this value at risk number. How far below the mean is this left tail? Okay, so the question is, where did this number come from? That's what we want to find out. So here we're just assuming that that was the result of our calculations, but now we want to know what those calculations are and where do we get them? All right. So, so we have a lot of assumptions. We can briefly touch on these. We know that we're assuming normal returns. Now, by the way, here's a really strong assumption. We're assuming that the returns are independent from one day to the next. So in other words, if we have huge losses to our portfolio today, it won't affect what happens tomorrow. Now, that's a tough assumption to live with. You know how markets tend to get into these trends when the markets are upset, they tend to lose money for several days in a row, don't they? When everybody's feeling good, they might make money several days in a row. So this assumption is necessary to make the framework manageable. Without this, the data needs, the computational requirements would be so astronomical that we might not even be able to do this. Okay, in other words, this is designed to make the framework manageable. Now, clearly, this is not correct, but is it enough of a problem that our whole framework is useless? And the answer seems to be no. At least the market doesn't think so. But yes, it is kind of a bizarre assumption. But again, it's made for a very valid reason. The alternative would be it would be unthinkably complicated. What else is it assuming? Well, usually assumptions are made about volatility. Now, volatility, as you remember, is how much an asset's value can change over time, or you could think of it as a measure of uncertainty or risk. And we usually measure volatility with the standard deviation. The statistical measure standard deviation is referred to in the financial markets as volatility when it refers to rates of return. We're also assuming that the statistical properties of the returns are not changing over time. So if you have a stock whose mean is 8% per year and their standard deviation is 20, we're assuming that that will still be the case over a given time frame. In other words, you don't want any changes in these assumptions. If they do tend to fluctuate over time, again, that's going to reduce the accuracy of our results. But this is what we're assuming, that they're fixed variables, that these don't change. Okay. If you're looking at a short time frame, this is not, I guess, a terrible assumption, but and again, it's designed to make things as simple as possible. Okay. By the way, the reason I'll tell you what, when you do make all these assumptions, what you're effectively doing here with your framework like this is you're saying, listen, we've got this normal distribution. You get some mean and some standard deviation, and the actual returns at the end of the day are just some random drawing from this distribution. Let's say today it's 0.01, and then tomorrow it's 0.023. And then the next day it's a loss of, let's say, 1.8%. So the outcomes from day to day are assumed to be drawn from this normal distribution with our specified mean and standard deviation. And so what you're effectively doing here is saying every day that goes by, the actual outcomes observed in the market are random drawings from the same probability distribution. And like with a roulette wheel, let's say, each spin of the wheel has no influence on the following spins. So that's what you're effectively doing. It's as if you're treating this whole thing as a big roulette wheel. Every day, a different number comes up in the wheel, but the wheel never changes. Okay, that's what we're assuming here. I think that's a good analogy. I like that. It's like a big roulette wheel is being spun in the sky, and that's generating returns to our stocks. Okay, I hope that clears up any confusion about what we're assuming here. All right, now, now here's one of the nice consequences of this simplifying assumption. One of the issues we run into with the value at risk is that the time frame that we're applying it to depends on the time frame of the data itself. What do I mean by that? So if our data is daily data, then the value at risk measure that we obtain is a daily value at risk. That's fine. So for some applications, it is important to have value at risk numbers as often as possible, every day if possible. So for example, for a proprietary trading desk, it's important to know soon as possible. If large losses are piling up. Yeah, we better find out. So that means for these cases, daily VAR is the most appropriate. Okay? Even if it takes the computers all night in Germany to calculate these numbers, daily VAR is the most appropriate measure of risk. But imagine instead that an insurance company owns a portfolio of government bonds. And these bonds are rare trading. So now, with an insurance company, you're trying to make sure you've got a decent rate of return, but you're not trying to take any terrible risks either. So you might have all these bonds that you almost never trade. You just buy them and you hold them. So for this example, in this case, it isn't really necessary to produce a value risk measure every single day because the value of the portfolio is not going to change very much from one day to the next. Instead, it might be sufficient to have a monthly. That might be enough to keep us informed about what's happening to the value of our position because the assets we have are simply not that volatile. And so what's the point? Now, here's the problem though. We're using daily data to come up with our measures. So for the second case with the insurance company is using daily data to obtain its value risk numbers. Well, how can it produce a monthly VAR? Well, that's where this next rule comes in. Based on the assumptions we've been looking at, we can use the so-called square root of time. Which says, and here it is, let me just copy this here. I don't know, hold on. There we go, we can copy this, I'm thinking. So we have this rule. So in other words, what you could do is say, listen, let's say we want a monthly VAR. Now, the VAR risk is based on volatility. So right now we're focusing our attention on the standard deviation. So we have a monthly VAR, a standard deviation rather. Here we have our daily. So if there are, let's say 22 trading days in a month, then this formula works as follows. We can multiply the daily VAR by the square root of 22 to give us the monthly, not the VAR, the standard deviation. Because the standard deviation increases proportionally with the square root of time. That's one of the properties of the standard deviation. It doesn't increase linearly with time itself, but with the square root of time. And so this rule is only made possible by all those extremely powerful assumptions that we've been making. Without those assumptions, this formula would be horrifically complicated. We would have to actually calculate the correlations between the returns from every day in our time series of data. In other words, we have to take into account the impact of each trading day on the next one in order to do this. Instead, by treating them as independent days, we can use this very, very simple rule. So we have our daily data. We want a monthly VAR, no problem. We multiply the daily volatility by the square root of 22, and the result is our monthly volatility. Excellent. All right, now the VAR formula itself is coming up very soon. Let's see what that's all about. By the way, let me just do one thing here. It drives me crazy that Word doesn't assume that you want page numbers. I don't know how would you not want page numbers? I mean, really. So now we're going to jump ahead a little bit and we're going to look at the actual formula. And you're going to say, wait a minute, it can't be that simple. Okay, so that's the actual value at risk formula. So only one thing really here requires some serious explanation. Let's see. There's only three terms. Um, this would be a superscript. So the first one is easy. V0 is the current value of the portfolio. Sigma is standard deviation right here. Oops. Now, why is it doing that? That's pretty frustrating. I didn't tell it to do that. Oh my God. Is the standard deviation or volatility of the asset in the portfolio. Now, this piece has a very specific role to play. It looks terribly complicated, but really what it is this. Yeah, we think of this as the location, or sometimes it's called a z-score, under the normal curve. Hold on. Associated with a confidence level of C. Now, because based on the properties of the normal distribution, there's really only three cases that we might encounter. So if we want a 90% confidence interval, or no, 90% bar, that means what we're looking for is and that number turns out to be minus 1.28. Now, you're probably saying, well, where did that come from? We're going to get that out of Excel. Okay. What it really refers to specifically is 1.28 standard deviations below the mean. For 95%, instead, we're going to find ourselves a little further out in the tail. That would be minus 1.645. And then for 99, and again, this is one of the properties of the normal distribution. We can look this up in Excel if you don't remember these. This tells me the location of the left 1% tail, or in other words, 99%. We're looking for 99% VAR. So you're actually looking for the dollar value that your portfolio could fall to at most 1% of the time. Okay, so the left tail can be attributed as a probability. In this case, it's 1%. And so we're saying that 1% of the time, our losses could reach that left tail. whatever that is. So here we're just looking at the normal curve, but then we later on can attach the other details and come up with a dollar amount. So this complex looking thing can be, it's the z-score. Okay, this is a very formal way of expressing the normal distribution. All right, so I think we're ready for our first full example from start to finish. Imagine that we own $10,000 worth of Hewlett Packard stock. Okay, so there's a single asset here. The stock's volatility or standard deviation is 1.89% per day. So we know a couple of things. Now they're telling us that we're trying to calculate the VAR, 5% VAR is the same thing as, oh, I just realized I'm not being consistent here, am I? Let me change this slightly. 10% VAR means we're 90% confidence. All right, let's write it like this because that's what I have in the slides. This next one is, we would call it 5% VAR, which means 95% confidence. And then down here at the bottom, we'll have 1% VAR, which means 99% confidence. All right. So that number, now here they're telling us we're looking for 5% VAR. So this term, which is our z-score, as you can see, is equal to minus 1.645. And believe it or not, the value of risk is just the product of those three numbers. $10,000, 0.0189, and negative 1.645.
Hey, Alan, how do you get the Z score here, the negative 1.645?
All right, so what's happening here is that you can get this in Excel.
Okay, there's no way to do it on the calculator, right?
Yes, there is. Which calculator do you have?
Just using the iPhone one.
No, it won't be there.
Okay.
If
It
you
does
have
everything
scientific,
else.
yes, I know it does. It's a very good calculator, but it doesn't have that. You would need a full-blown scientific calculator.
Yeah.
Excel can actually handle this very easily. Here's what you have to do. As a matter of fact, it's actually here in this. You wouldn't even need a new example. This document is called normal distribution. And so
Okay.
here, the function, as you can see, is called norm.s.inv, which means the inverse of the standard normal distribution. The 0.05 means we're looking at the left 5% tail. And so the Excel comes back with a value negative 1.645. So that's how you would actually calculate it. So you can think of it as how far away from the mean are we in terms of standard deviations. So like imagine yourself taking a test and somebody tells you that your score, here's the mean, is 1.645 standard deviations below the mean. That means you didn't do very well at all. That's the boundary between the bottom 5% and the upper 95%. So when you're dealing with the normal distribution, you're thinking in terms of not like dollars or anything like that. You're thinking in terms of standard deviations above and below the mean. How far away are we from the center of this distribution? Okay. Now you can apply units if you want. Like imagine if these are dollars, then you have to be told though what the mean and standard deviation are. So here's a good example of this. Imagine I told you that, suppose that the mean, that the scores on an exam are normally distributed. With a mean of, let's say, 80 and a standard deviation of 5. That means if you rewrite this graph in terms of
0.2.
the mean is 80, and then the bottom 5% translates into 80 minus 1.645 times 5, which is approximately let's see, 1.645. It's about 71 point, say, 70. So if that's your score in the test, that means you only outperformed 5% of the class. You did worse than the other 95%. So you might remember when you take standardized exams like the SAT or the LSAT or whatever, they always give you your score as a raw score. They also give you a percentile of some kind. So in other words, here, this would be thought of as the 5th percentile for this distribution. That 71.78 means you're in the bottom 5% because you're 1.645 standard deviations below the mean. So yeah, the normal distribution makes it possible to compare directly measures from, with different values like scores or heights or weights or, incomes or whatever the case may be, in terms of a common metric, which is the standard deviations above and below the mean. Then you can convert it to units if you need to do so.
Well, how about you on the other side? So if you were above the mean, it would be
Well, let's see. With that happy case would be
yeah.
80 plus 1.645
Right.
times 5. It's going to be approximately 88.225. So that would put you in the top 5% of the class. Happy then. Okay, so in other words, and again, you notice the symmetry. The two tails have an area of 5%. Oh, I'm sorry, I wrote this incorrectly. This should have said mu plus 1.645 standard deviations. There we go. All right, now we're good. Now you can figure out all of these directly in Excel. So, and we'll do a lot of that too. So, like for example, if you were told, again, we'll do the same thing here. We've got the mean is 80, the standard deviation is 5. The probability. What you can look for is the z-score that corresponds with a lower 5% tail, and the z-score corresponds to the upper 95%. And the way to do that would be norm dot ein phi. The probability here is 5. Mean is 80. Standard deviation is 5. And that just is exactly what I just showed you on the calculator. Oh, wait a minute, what happened here? Oh, I know what. These two need to have dollar signs to anchor them in place. And so that's exactly what we got with the calculator. Okay, and you could use any of these. Like I could look for the bottom 10. Watch how easy this is. The upper 10, that kind of thing, just by changing this z-score. So these are areas under the curve to the left of that point. These are the corresponding values. Okay. So we'll be using that for whenever you have a model like this that's based on the normal distribution, this is exactly how it's done. Okay. All right. So anyway, I think let's go back to slides for a minute. I think we have an example waiting for us. Oh, it's this example, right? We didn't quite finish it. Given this information, we're being told if you multiply those together, you get $310.90.5, which means that over a single trading day, let's draw this somewhere. If you're 5% VAR, it's $310 and 905 cents. Whereas your original mean or the current value of your portfolio was $10,000. Then this is what you're looking at. The difference between these two, and that means right here, that's the threshold between the lower 5% of this distribution and the upper 95%. So right here, that means 5% of the time our losses, our value of our portfolio will hit 96.89.095 or possibly worse. So this 310, this is the actual value at risk right here at the 95% level of confidence, or sometimes we call it the 5% VAR because it refers to the left 5% tail of the distribution. So that's how much we could lose potentially every day that goes by. This is really the, oh, sure, go ahead.
Kind of for my notes purposes, I may have missed this when you were on the Excel sheet.
Right.
Can you explain again the relationship between the z-scores and the percentile in a normal distribution?
Yes. So what's going to happen here is that there's several that are kind of important. If this is this is your mean, that means this distribution is half of it is below the mean and half is above. Now, for let's say the bottom 10%, let's assume the mean is 0. 1.28 standard deviations below the mean results in the left 10% tail. So here I'm assuming that the mean is 0 and the standard deviation is 1. So therefore, 1.28 standard deviations below the mean is actually the number negative 1.28. That's my threshold between the lower 10% and the upper 90%. And if we're interested in the bottom 5%, we would have that would be the mean minus 1.645 standard deviations, which in this case would be simply be because we're assuming with this model that the mean of this distribution we're using is 0 and the standard deviation is 1. That, by the way, is my so-called z-score, which is how far away am I to this away from the center in terms of standard deviations. You may have heard this term. And then for the bottom 1%, we're interested in, and by the way, these are really the 3 cases you're most likely to run into. The others, in principle, you can have any left tail you want, but you're not likely to run into this, the others very often. 2.33 standard deviations below the mean puts us at the left 1% tail. And those are the only 3 that you really need to remember because those are the ones you're most likely to run into. Okay. No, yeah, I mean, there's plenty of others. If you want to look them up in Excel, you certainly can. And how do I know those numbers? You could go back to the Excel spreadsheet we started to look at, say, all right, suppose we're looking for the left tail area of 10%, 5%, and 1%. The z-scores, according to Excel, are going to be norm.s.ib. This number. Oops. And except for the rounding, you can see that's exactly what I just showed you. Okay. That tells me how many standard deviations we are below the mean when we're at the left 10 percentile, the left 5%, and the left 1%. Now, this application is only really focused in the left tail. You might say, well, what's going on in the right tail? With value at risk, remember, we're trying to see how much loss we're potentially exposed to. So we rarely consider the right tail. It's the left tail because that's where all the losses are. Yeah, because I mean, it's meant to be a very conservative measure. If you make money, that's wonderful, but we're trying to understand how much we might lose at a given time. Okay, so that's why we're doing it this way. We're only considering the left tail of this distribution. Anyway, so all of this helps us understand what this formula is really doing. So here's the thing, with this Hewlett-Packard case, where again, we have a value of 10,000 and the z-score for left 5% tail is this 1.645, and the standard deviation, as we were told in the problem, is 0.0189. The value risk with 95% confidence or 5% R is simply the product of these three. Which is approximately 310. There's some rounding differences because but it's approximately 310, $311. And then that means the interpretation is that our losses can exceed this number no more than 5% of the time. Now, since the data used to obtain these numbers is daily, this VAR of 310. By the way, we usually express VARs as a positive number, even though we know that it's a loss. We usually would call this VAR positive 310 just because it's understood that it's a loss. Okay, so the VAR approximately 310.87 or whatever is the daily value risk of this portfolio. If we want to know the monthly VAR, for some reason, we can multiply this result by the square root of 22. Since this is a common assumption, and Hull's book does this, a common assumption for the number of trading days in a month. And that would give us, so the monthly VAR at the 95% level confidence would be the 310 times the square root of 22, which brings it up to about $1,458. And then based on that logic, the annual VAR at the 95% level of confidence would then be multiplied by the square root of 252 is the number that we normally see. And again, this is something that Hull's book uses. About 49.35. Note, John Hull's book uses 22 days in a month, trading days, that is. 252 trading days in a year. There's you could try others. It's not the same every year, obviously, or every month. It depends on, how many holidays there are, whether it's a leap year and all this and that. So it's never going to be the same two years in a row. But Hull apparently believes that that's the best one to use. This is what he sticks with. Okay. All right. So we now know how to calculate the value risk for a portfolio at a given level of confidence on a daily basis, on a weekly. Well, we haven't done weekly, but if you did, it would be the square root of 5 because there's 5 trading days in a week, monthly and annually. Usually these are the numbers that you see in the market daily or possibly monthly. You don't normally run into some of the other ones, but it's always possible. Okay, using our square root of time rule. Now, sometimes we don't really need to know the dollar amount. Like if I want to compare two portfolios directly to each other, we have this concept called, well, what we just did was called dollar, which means the results are measured in dollars, obviously. Okay. And that's fine as far as it goes. But sometimes it's hard to compare two portfolios. Let's say you have two portfolios, but one of them has $1 million worth of stock in it, and the other one has $100,000 worth of stock. Well, you don't want to compare them with each other because keep in mind, the higher the VAR of a portfolio or stock, the riskier is the stock or the portfolio. So if I'm going to go ahead and compare $1 million portfolio with a $100,000 portfolio, of course, the numbers will make it always look like the $1 million portfolio is the riskier of the two. I don't want that. So how do I directly compare them to each other? Oh God. I notice sometimes when I copy and paste, well, that's just plain weird. It's supposed to let me create subs. I don't understand why this is happening. The damn thing is grayed out. All right, we'll get to that later. Anyway, so instead, in order to directly compare the VARs of two stocks or portfolios, we can use what's called percentage VAR, where you basically the dollar value of the portfolio is left out. That's the only way you can compare them directly to each other. So for example, here, you can see we've left out the V0 so that, maybe we can make up an example. For example, suppose that portfolio A has a volatility of 20% per year. Portfolio B has a volatility of 30% per year. Clearly, it is the riskier of the two. All right. So the percentage VAR for the first one on an annual, let's keep it simple, an annual basis is, at the 95% level of confidence. On an annual basis would be, and so you're just going to literally multiply negative 1.645 because it's the left 5% tail and put 2.0, and you're going to get negative 0.329, but of course we often drop the negative, and that's a percentage. Oh, this stupid thing. Oh. Oh, I know why it's upset. Hold on a second. You gotta watch it with this. If you try to lead off any statement in Excel with a negative, you'll confuse it. All right, that's portfolio A. And then for portfolio B, the only thing that'll change, because we're looking at the 95% confidence level in both cases, is that you'll change the volatility, because that's the only other variable in there, to 30. And that's gonna bring me to oh, hold on. Uh, 49.35, let's say. All right, so I mean, it should be pretty obvious that if we're measuring them both at the 95% level of confidence, the one with the higher volatility is the riskier one. But if I then mix in dollars, you can see how I might get the wrong opinion. If the riskier one has less money invested in it, it might appear with the dollar VAR that it's the safer, but it really isn't. Okay, so this refers to the chance of this returns deviating from the mean by this much, essentially. All right. Now, what about portfolio VAR? This is where it gets interesting. So far, we've only considered a single asset. What about two or more? How do we compute value
Hey,
risk?
before we move forward there,
Yeah.
the previous example is just looking at two separate stocks,
Yes.
essentially. So one
Yes.
stock just has a higher volatility. That's the only difference in this scenario.
That's correct.
Okay, but it doesn't
Yeah.
take into account external factors.
Well, the value risk methodology only considers these factors. It's all been, as far as it's concerned, the volatility already reflects all those factors that you're alluding to. And now remember, this whole thing is designed to be straightforward, simple, easy to calculate.
Yep.
If, for example, the first stock or first portfolio, the owner was just sentenced to life for stealing all the company's money, that should be
Yeah.
reflected in the
Might have to
volatility.
reset that volatility. Yeah.
Right. Tomorrow, the volatility will be 90%. And then that means this one will be infinitely riskier because the president tried to get on a plane to Peru with all the company's money, and that was the end of that.
Got it. Okay. Yeah, it already accounts for it. Okay.
You never know what might happen in some of these places.
Right. This is just directional.
Right, exactly. Now, the tricky part here, and this is where, by the way, this is where the portfolio theory gets involved. This is where Harry Markowitz's framework starts to get involved. A single asset is easy. You start talking about two assets even, and it starts to get quite messy because we must take into account the weights or proportions of the portfolio held in each asset. And we must consider how closely these assets track each other, I guess we'll call it, as measured by the correlation between them. Oh my God. Now we're getting some very, very deep waters. Now, let me just give you a quick side look at correlation is a measure. I'll put this back here. Correlation is a measure of how closely two assets track each other. Or another way of thinking of it is do the assets tend to rise at the same time, fall at the same time, or move in different directions? That's very, very intuitive. There's nothing the least bit rigorous about that, but let me give you a few examples here. Now, first of all, the correlation measure itself, which is built into Excel, by the way. If you, let's say, we throw together a couple of stocks. Stock A, stock B. And let's say over the last 5 years, the returns were negative 0.03, 5, 2, wait, 1, 4, and 0.1. Over here, this stock. No, I'm at positive 6. Now, if you notice, if I were to draw a graph of these two, you'll notice something interesting. They tend, all right, well, maybe not the ideal graph, but if you notice, they do seem to follow each other very closely, don't they? Okay, they both tend to do well in the same years. They both tend to do poorly in the same years. So the correlation between these two would tend to indicate that they're very closely related to each other. So we're going to calculate the correlation measure in Excel, and we're going to see that it's, wow. Now, the reason why that's such a high number is because of correlation ranges between -1 and +1. That's all we have. Okay, so -1 indicates that two variables always move in opposite directions. +1 indicates that two variables always move in the same direction. And then in 0 indicates two variables are unrelated to each other or they're independent. Okay, then we have everything in between. And so if you were to draw the special type of graph called a scatter plot, it might be easier to see this. Well, actually, with so few points, it's hard to tell. But let me just draw you a little illustration back here. Here. All right, here we go. So if you have two variables that look like this, now these points that I'm about to draw in here represent returns in different years to the two stocks X and Y. You can see here the points have a positive slope. If you draw a trend line through here, that means that there's a tendency for both of these to go up or down at the same time. So here the correlation is positive, meaning there's a tendency for them both to move in the same direction. Whereas if it's the opposite, you'll get something like this. This is my trend line, and you can see it as a negative slope. The correlation is negative. All right, and then finally we can have the case where they're just plain unrelated to each other. And if that happens, they're just randomly scattered about the axes, and then the trend line will simply be flat. So here the correlation is equal to 0. So that's basically the three cases we might run into. They're either positively correlated, meaning they tend to move together. They're negatively correlated, they tend to move in different directions. And in the last case, they're simply unrelated to each other. And in fact, matter of fact, an important component of modern portfolio theory is that the lower is the correlation between the assets in the portfolio, the lower will be the risk of the entire portfolio. since the portfolio will be more, and we put this in quotes, diversified. In other words, if you have a portfolio that has stocks from all over the economy, we have some oil stocks and manufacturing stocks and retail, then we have a diversified portfolio, which means the correlations tend to be fairly low, and that helps reduce the amount of risk that we have in our portfolio. Whereas if we bought all oil stocks, we'd be in a situation like this, and there's essentially no risk reduction. So when you have two assets in your portfolio, this has to be explicitly considered. So now here's a portfolio, stock X, stock Y, and the amounts are different. By the way, I just made up these numbers. So you'll see that we can fill these into a formula, but the important thing here is that we've got between the two stocks. Here we go. So in this example we're about to tackle, we have $60,000 worth of stock X. And the rest is in stock Y. So the weight of stock X is 40% because that's the total percentage of the portfolio that is in stock X. In other words, 60%. This is 40%. Those are our weights. And then we have these data are given to us. The standard deviation of X is 0.016284. The standard deviation of Y is 0.015380. The correlation between them is negative 0.190550. So that means there's a slight tendency for X and Y to move in opposite directions. Okay. What are we going to do with all this information? Well, here's what we have to do. The portfolio VAR is going to be written in the following way. Let me copy this formula real fast. No, I'll write it. It's fine. So it's going to look very similar to what we did before. Except for one little detail. That's it right there. So the portfolio has its own standard deviation, which is a weighted average of the standard deviations of the two individual stocks. So the question is, how do I calculate the standard deviation for the entire portfolio? And you're going to be kind of scared when you see this formula. But we'll plow ahead anyway. And this is, by the way, this is Markowitz's work that we're looking at here. This is sigma X, this is sigma Y, this is rho, the Greek letter rho. I think I put it in here. Yeah, this is the Greek letter rho. It is normally used to measure correlation. And so this is the formula. For calculating the standard deviation of a two asset portfolio. Oh my God. So you can see, this is one of the reasons why VAR takes so long. It's unbelievable. Look at that. To go from 1 to 2 assets, look how much work I have to do to calculate the standard deviation of this portfolio. So here's what I'm going to do. Let me just quickly run through it here. Y squared. Stop it. This really is annoying me. So we have the weight squared, we have the standard deviation squared for X, and we do the same thing for Y. C62 squared times C63 squared. Then we need the last term, which is 2 times B62, C62. Correlation is B64. The two standard deviations are B63 and B64. It's approximately 2%. Oh, now wait a minute, something's not right. Point 6, 0.16284, 40%, 0.1538, negative 0.19055. Let me try that again. I don't know what the problem is here. It's, oh, wait a minute. You know what I just realized? I forgot the two. No, I didn't. It's all there. All right. Well, all right, forget that. Just let's just say that it's 2%. See, no, that can't be right because it would be lower than what the hell is going on? The square root of B62 squared, B63 squared, plus the same thing for the y's, C62 squared, C63 squared, plus 2 times the two weights, the correlation, then the two standard deviations, which are B. God, I have no idea what happened. These are the right numbers. Two times the two weights, the correlation, and the two standard deviations. Let me try something. I have no idea what the problem. All right, let's just leave it like this for now. This is the standard deviation of the entire portfolio, which means the portfolio VAR would be the value of the portfolio, which I don't see it here. I think it's $1 million, $100,000. And we're trying to do this at the 95% confidence level. So therefore, the z-score, as we saw earlier, is approximately negative 1.645. That's only an approximation. And then the standard deviation is this number, which I think it's right, but I'm not sure because the slides show me something else. But anyway, the portfolio VAR would be the product of these three numbers, the $100,000 times the z-score times the portfolio standard deviation, and that's about 33 something according to this, and it's negative, which is what you would expect. But often we report it as a positive number, so I can just put a negative here. So this is the part that is taken directly from Harry Markowitz's portfolio theory. This calculation of a standard deviation for not one, but two or more assets in the same portfolio, which, like I said, we have to take into account the weights, meaning the percentage of each asset in the portfolio, and the correlation between them, which is in this case negative 0.19055. Wow. So you can see now, imagine if there were three assets or four or five. That starts to get into territory where we would have to resort to another branch of mathematics for three or more assets. We normally use a branch of mathematics, which you may have heard of it, called matrix algebra. Does that ring any bells? And by the way, Excel does have the ability to carry out matrix algebra operations. I don't think we'll have time to do that here, but it does have that capability, believe it or not. I mean, it's really a very powerful package. And once you have that, you can extend it with the square root of time rule to anything that you want. Okay. So now what they sometimes you hear this this measure called this is sometimes called diversified VAR, means the value at risk actually obtained from actual data. Then we also have this other notion called non-diversified VAR, which means the value at risk obtained if we assume that the correlation is 1. Now, in other words, no benefits of diversification. Now, the difference between the two, non-diversified is the larger of the two, minus diversified VAR is referred sometimes as the benefits of diversification. Okay, notice they're trying to show you how much risk you're reducing in your portfolio by holding the right set of assets, meaning, and by the way, just as a side note, the lower is the correlation coefficient, the greater will be, well, I should say the more diversified will be the portfolio, and the greater will be the benefits of diversification. So in other words, if you're choosing a portfolio, you don't want all of them to come from the same industry, because then the correlations will be quite high. You want to have a mixture of different industries to be exposed to, let's say, or different kinds of stocks, like large cap and small cap and that type of thing, or from maybe even different countries, whatever it takes to make sure that you're not exposed completely to one set of risk factors. Okay. Now, let's see, what else do they have for us here? Now, there are other more complicated, we're going to try to skip over these more complicated cases. I'd rather jump ahead to one of these other spreadsheets that I put in there. It turns out that there are ways we can extend VAR to give us a better look at our how much risk we're actually exposed to. Oh, look at this. I forgot this was here. One of the spreadsheets that I produced for you is this one. And what we have here is these 3 stocks, and we have 3 returns, 3 risks, 3 standard deviations, 3 correlations. You could use this if you wanted to construct a 3 asset portfolio if you saw fit. Once you chose some weights, But what I want you to see here is that I've already done this for you. This one is 50% A and B, 50% A and C. This is 50% B and C. Now, what I want you to see is that these are the returns and these are the risks. So if you notice, A and C have an extremely low level of risk because the correlation between them is negative. Whereas here, A and B have a very high level of risk because they have the highest correlation between them. So while this one gives you an average return of 12.5% versus 11, the risk is like 7 times as great. Okay, so you might want to think twice about buying portfolio A. You might be better off with AC rather, or possibly BC. And so you're getting all this reduction in risk because of the correlation. That's where it's coming from. Okay. All right. Let's see. Now, also, another interesting thing here we have is this concept of expected shortfall. So in a nutshell, what's happening here, let me just put this in this document. One of the drawbacks of the value risk measure is that it only tells us the losses that occur, that can occur once we reach the left tail, X percentile of the distribution. All right, so in other words, imagine this is your situation. You've got some asset or some portfolio, and you're told that, you know what, if your portfolio starts out at $1 million, the left 5% tells here, let's say this is 900,000. The value risk here is equal to 100,000. 95% confidence level. Now, what is missing here is we don't really have any sense of how large our losses could get if we continue to move into that left tail. It's just all we're being told is the threshold to that left 5% tail. What if we need more information about the possible losses that could occur if we reach the left tail? And by the way, so the way the market's been going the last week or so, I'm sure a lot of value risk models were, we reached this threshold easily. One day, didn't the market drop like 2,000 points one day? It was going low, very low. So that means you probably have these models where you've got something like this. Got $1 million portfolio, and you think that, well, you know, we're in pretty good shape here. The left 5% tail is here, and 95% confidence level. Our bar is 100,000, and then all of a sudden you wake up one day and we're out here somewhere, and we're down to 700,000. Like, what happened? See, this is one of the drawbacks to models like this, is that it's difficult to tell what kind of extreme outcomes are possible. We're looking at averages here. On average, once a month, we might get down to 900,000 or so. So some extensions of VAR have been developed where we're basically focusing all of our attention on the left tail itself. Because one of the unfortunate things about VAR, the way it's set up, I don't think I mentioned this earlier. I'll mention that right now because it's important. Is that it tends to underestimate the true probability of extreme losses. Which is kind of unfortunate because that's kind of what it's for. It's trying to help us identify chances of losing enormous amounts of money. So another kind of extension of VAR was created at some point. I don't remember who's responsible for this, but in order to better understand the behavior of the left tail, the measure expected shortfall can be used, or ES can be used. This with expected shortfall, the value at risk is calculated with several levels of confidence in the left tail and then averaged out. In other words, you might, for example, do something like this. So this loss of 10,000 is my VAR at the 95% level of confidence. And then all of a sudden we might have 88,000. That's the VAR at the 96% level of confidence. Try it again for 97. Maybe that brings me down to 86,000. So you see what's happening here is we're moving deeper and deeper into the left tail. And then we're going to average them out. So let's say we decide in advance, suppose we calculate the VAR with levels of confidence of, let's say, 95.5. And that turns out to be 12,000. 96, 14,000, 96.5, 15,500, 97%, 17,200, and then finally 97.5%, 20,100. The average of these is, let me just quickly throw that in the calculator, 12,000, 14,000, 15,500, 17,200, 20,100 divided by 5 is 15,760. And so that means that, and let's just say that, suppose that the 95% VAR is 10,000. So what this means is that, so this is our expected shortfall. And that means that 5% of the time, our losses can exceed $10,000 if we reach the left tail. On average, our losses will be 15,760. So you can see that's actually a pretty useful information, more than just telling us that the VAR is 10,000. In addition to that, the average loss that we experienced in that left tail is about 15,760. So you can see it's a very useful complementary measure to the value at risk. Now, of course, we have to make decisions about like how many of these do we calculate, et cetera, but you get the idea. It's just designed to help us have more useful insights into how much risk we're exposed to. Okay, so this is what expected shortfall is all about. A way of improving the value at risk methodology. All right, now I think there's a spreadsheet hiding in here where we can do some actual calculations. I've been saving this all night. That would be, let's see. Oh, it's this one. The title of this document is Value at Risk Example. So basically, what you're seeing here is a work through example for these two stocks, V and Q. And let's just quickly run through it. All right, there's, the work has already been done, but let's just interpret what we're seeing here. So we got 10 years worth of data. We got closing prices, we got dividends. The HPR, by the way, stands for holding period return. It's equal to the dividend plus the capital gain or loss, all divided by the original price of the stock. Okay, now we're going to do that for all of those years in our data set for both Q and V. At the bottom here, you're going to see some familiar numbers. The average return or expected return is the Excel function average. The variance, it's called var.s because this is a sample of data as opposed to a population. And then the standard deviation is, the command is called stdev.s, which means sample standard deviation. Over here, we did the same thing for Q. Now, if you notice, we also have the covariance between X and Y, not X and Y, in this case, V and Q, and then the correlation, although this is really the one that we need. Okay, so the Excel command for that is correl. And here's our old friend, the standard deviation of a 2-asset portfolio. So if we assume half of our money is going to stock V and the other half in stock Q, these are just copies of this information from up here. So they're all in one convenient location. What we've done here is this. The expected return of the entire portfolio is about 3.8%. This number here is this formula that we just used a little while ago. This is Markowitz's formula. So if you want to go back and double check these in Excel, you can. If we sat here and did this ourselves, it might take a while, but it's already done for you. So you can go back and double check and confirm the results. So over here, we're assuming that the portfolio is worth $1 million. By the way, the word quantile means standard deviations below the mean. Except that we usually write it as a positive number. It's actually negative, but it's normal with the value at risk methodology to use that as a positive number because, again, it's understood that this is a loss. So that's our old friend 1.645, which is the borderline between the lowered 5% and the upper 95% of the normal distribution. The portfolio standard deviation is copied from here, where we use Markowitz's formula. And the product of these three, now, by the way, this is yearly data. So the value at risk that I obtained here is a yearly VAR. All right. Now, we already saw earlier that if we don't like that, we can scale it with the square root of time, except here, if I want to shrink it up to the monthly VAR, I'm going to divide by the square root of 12 because there's 12 months in the year. And then to turn it into a daily number, I'm going to divide by the square root of 252 because there's 252, we're assuming 252 trading days in a year. Now, as far as this diversification thing goes, if you want to know how much you're benefiting from having stocks with such a low correlation, which is, where did it go? Here it is. That's very close to zero. What you're actually doing is your undiversified VAR is based on the assumption that the correlation between them is 1. This is based on the actual correlation, and the difference between the two is 18,000 something, which means we call it the benefits of diversification. So this would be an example of how we would determine the VAR of a 2-asset portfolio. And if we want, we can experiment with it and change our assumptions. We could change the correlation, for example. We could do all kinds of things. And so you can see it's easy to come up with the results that we need. But again, this is limited to only 2 assets. If we have more, it gets a lot messier, but it illustrates what we're doing with value at risk. Wow, this is a fairly complicated topic, isn't it? Now, what does this have to do, by the way, with options and futures? Well, we can calculate the value at risk for an option, although it's a horribly complicated process. And by doing that, we can figure out if we buy an option to hedge the risk of these two stocks, we can figure out how much it adds or subtracts from the VAR of the entire portfolio. Okay, so we're not going to have time to get into that tonight because it's a very messy process. But when you do buy an option, you might want to know, well, how much did I just reduce my value at risk? And so it is possible to do exactly that. But again, it's a very messy process. So we won't have time to do it here. But any derivatives that you have in your portfolio will have their own value at risk. And so you can add that to the portfolio and see how much it impacts on your on the risk of the portfolio in terms of value at risk. So if you're thinking about hedging your portfolio with an option, you can figure out easily what an impact it's likely to have on your value at risk with these measures. Okay, so well, anyway, I think that let's see if there's any other spreadsheets that we have here. Yeah, I didn't think I was going to make it tonight. I didn't, but I'm here. This came on me very suddenly, I must say. It'd be nice. This morning, I actually had frost on my windshield. I was driving to school, and I did not appreciate that. I mean, for God's sakes, isn't it April or what? Okay, no, we don't want this. None of this crap. So anyway, so we got all these results here. We've got all these spreadsheets. I have to organize them and post the results in Brightspace, but I think we pretty much have covered everything we wanted to do here. And if you wanted to take this to another level, you'd probably have to take a whole entire course in value at risk methodology because it is a very complicated subject. But at least we have a feel for what it's all about and what we're supposed to do with it. So I thought it was a fitting way to wrap up a course like this because ultimately what we're trying to do here with these derivatives is hedge our risk. So this gives us a framework for telling us how much risk reduction we're actually getting from a given set of assets and derivatives. So anyway, so I think we're going to have to stop right here. And I'll be posting all these results and I'll be working on your homeworks over the weekend. Although they look good so far. I mean, sure, everyone's fine, but I just want to go through them one more time. And then early next week, I'll start posting the grades as soon as I have them. And you should be able to see them in Brightspace once they're ready. Okay, so now I don't know what you're going to take next. What else do you have on that schedule? Oh, all right. Aren't you working towards a certificate of some kind?
Yeah, I think there's a mergers and acquisitions. There's an accounting one, and a couple others that are available.
So,
Yeah, I'm
the
actually
mergers and
finishing up with mine.
acquisitions, which one are you taking?
I'm finishing up with mine now.
Oh, okay.
Your class is my third, and then I
Okay.
have valuation that I'm currently in.
Ah, okay. But yeah, I've actually I have a little background in mergers and acquisition. It's a very interesting area because you don't see a lot of mergers in the real world. But that one depends very heavily on being able to analyze the value of the takeover of the company you're trying to take over. And it's a very specialized area of study, but it depends very heavily on being able to analyze a company's financial statements. So if you're good at that kind of thing, you'll also be very good at mergers and acquisitions. Or if it's because you're basically analyzing equities, you probably won't run into derivatives in that class, which is sad, but you will
Jonah,
try.
how's the valuation class?
I'm not quite
So
sure
far,
what they're
so good. It's
what are they
actually
doing in
pretty
that
good.
class. What are
Right
they
now,
about?
okay, right now we're doing a project where we're comparing publicly traded companies.
Oh, really?
Uh yeah, it's we just did, hold on, let me pull something up really quick. Uh We just did a quiz, which I actually got 100 on because by default, actually, he left off some information on the first question, which was worth 30 points. And because of that, he gave us the full credit.
Awesome.
Yeah, it's pretty cool. So I'm not sure how much I think, with all the information, I would have probably gotten an all right score, but 100 is not bad, right? One
Yeah.
sec.
By the
Wanted
way,
to.
I do have a recommendation for anyone who's taking mergers and acquisitions. If you were to go to YouTube,
Mhm.
there was a very famous book about 30 years ago called let me just show you may have heard of this book,
Right. Uh,
Barbarians at the Gate. It's about the takeover war. There's a leveraged buyout of if I'm remembering correctly, Nabisco. I'm starting to forget all the details, but the reason why I recommend this is because if you're learning about mergers and acquisitions, this is actually a leveraged buyout, which is a type of mergers and acquisition, except that it's a hostile one. And there's a bidding war between two parties to try to acquire control. And it's a true story, but they made the movie that they made out of it is so well done. It'll help you understand exactly what was going on at this time, which is, I think, if I remember, in the early 90s. So I'm sure you can get a copy of it on, or let's see, it's probably on YouTube. I don't normally make recommendations like this, but this one is so wonderful. There's some fairly famous people in it. The story of Ross Johnson's Nabisco takeover. It's about an hour and a half, an hour and 45. And it's just so well done. They explain what they're doing. What happened was ultimately the winner of this bidding war had to issue a lot of debts to to acquire RJ and Nabisco, and you can see the consequences of all that. But it's just that it gives you the human side of the story too. These powerful men who are fighting with each other over control over this company, and it gets to the point where it's more than just finance. It's all about pride, and but it's a true story, and the movie was made. It's very well done, and so it would be a perfect thing to watch in a mergers and acquisitions class.
The
Okay,
book is a tidy 624 pages.
that's right. So you might, if you're short on time, especially like after you have a new baby, for example, you
Yeah.
might want to just spend 2 hours watching this documentary. You'll be fine. Unless you really want to look at all the gruesome details. I think you'll agree. This, just watch it and you'll see it. You'll really enjoy it. Even if you're not taking mergers and acquisitions, I think you'll like this very much. That's
Awesome.
my recommendation.
Well, thank you very much. Appreciate the time in the class, and
Yeah,
look forward.
this is
I'll
one of
get you
my
that
favorite
get you that
classes.
homework.
Yeah, because sorry, I just can't stand being sick here, but yeah, it was a lot of fun. So there's a lot of topics to cover. There's a lot of we're drawing in stuff from all over the place. We got a lot of math and statistics and everything, but unfortunately, we can only cram in so much in 8 weeks. So but on the other hand, you have all this background now that you didn't have before, and so what else can you ask for? I mean, really,
Mm.
hopefully it was interesting at least. Or if not fun, maybe fun is pushing it, but at least your Excel skills would go up, your statistics skills, all kinds of interesting things that you might not have run across before.
Definitely helpful for evaluating options. That's for sure.
Very much so. Yes.
Mhm.
Yeah. Because, you can it kind of shows that's one of my favorite things is options. I find that equities are not so interesting. That's my personal opinion, but options are extremely exciting to me. And so that's just the way it is. Okay.
Yeah,
So
I
all right,
currently sell and buy options in my
you
portfolio
do.
now. Yeah.
Oh boy. Oh my God.
So
I'm
I'm
so
just trying to make premiums and make premium and rinse and repeat, and then obviously buy where I think it makes sense. But I do it in a basically a year long
uh-huh.
buy a call option, so it gives
Right.
time for the company to develop.
Right, of course, because you have all that time value. And
Exactly.
are they going to let you trade at home when the baby's been born? I mean, work at home.
Yeah, well, I work at home most of the time. I go into
Oh,
Midtown once a week,
oh, I see.
but my job
You know
has
what?
nothing to do with finance or derivatives of anything like
Oh,
that.
I see. Oh,
Yeah.
okay. I actually know somebody who works in the field. I don't remember exactly what he does. It's definitely finance, but I saw him the other day for the first time in quite a long time, and I was surprised that he told me that his company is still working at home. It's not because they can't come back. It's just because the company is so small. There's hardly any point in renting office space for like such a small company. And so they do their business at home and everybody's happy with it.
Yep.
Why do you need an office? I mean, really, you know, so anyway, all right. So I'm got, like I said, I mean, I hope you had fun with this class and all the notes are still in Brightspace. They won't disappear. I think well, I'm not sure how long you'll have access. I'll tell you what, if you later down the road discover that you forgot to download some of the notes that you wish you had, you can just send me an email and I'll send it to you.
Awesome.
All right.
Thanks,
Yeah.
Alan.
I'm not going anywhere.
Alex, by the way, I sent you the syllabus just in case you wanted to look over that class. I emailed it to you. So you can
Thank
have
you.
that. Yeah.
Yeah, I think it's going to be a while before I need two more classes to get the certificate, but now that we have two children here,
Oh, this is the second.
Congratulations.
Oh,
thank you, thank you. Yeah, I have
oh
a
my
3-year-old
God.
daughter and my son is 2 weeks old. So,
Two
Ooh,
weeks. Oh my God. Congrats.
thanks.
that's
It's
wonderful.
taking
But
3 hours once a week doesn't seem like it's a lot, but we had to actually hire our babysitter to come today to put one of our kids to bed so I could take this class. So
wow.
Yeah.
Yeah.
I got to do
I have
like
an
one
11-year-old,
class.
so I get it.
Oh, yeah,
I get it.
you've
Yeah,
been
I
there.
see it. Wow.
Yeah. My valuation class, I actually take it from a basketball gym.
Oh,
Wow.
it's
You have
amazing
to
you're able
stay.
to actually get it in, man, because
Yeah.
it's tough to do two of these, to do it twice a week.
Yeah, it is very tough, and then I'm a single parent with him. So,
Oh my
I
God.
yeah, and I work
Wow.
at NYU Bursar's office. So I
Uh-huh.
get home at
Oh,
6
you
and
got
just
that
log
inside
right in.
track.
That's right. I hope that means they're paying for this.
Yeah, it's covered.
Oh, okay, good.
Yeah.
Yeah. Yeah, all right. All right. So I'm going to wish you all a good night and good luck.
Thank
And if you
you.
All the
haven't sent
best.
in all
Thank
your
you.
assignments yet, you can continue to do so for a while, and I'll try to have the grades
Okay.
ready by early next week.
All
Okay.
right.
Sounds
Thank
good.
All
you.
right.
Thank
Good night,
you. Bye,
everyone.
everybody.
All right. Bye.
Bye-bye.